Hello everyone, this is Haoyang Lu from the University of Tennessee. Our paper is supporting real-time wireless traffic through a high-throughput side channel, and this paper is co-authored with my advisor, Dr. Wei Gao. First, I'd like to thank Dr. Tosley for his keynote yesterday. Now, his lecture yesterday made my presentation much easier since there are some similar stories. The development of network techniques have given birth to a lot of applications, and these applications fundamentally changed our lives. So among these applications, part of the application require the user requests to be delivered timely. And this traffic are real-time or delay-sensitive traffic, and any delay will degrade the user experience significantly. So another type of traffic are throughput, bandwidth demanding traffic. They require high throughput and will occupy lots of the bandwidth resources. So if there is only real-time traffic, then the data generated can be delivered timely after its generation, and there will be no delay. However, if there are other types of traffic, especially delay-sensitive or bandwidth-demanding traffic, then the delay-sensitive or real-time traffic cannot be delivered timely, and it will be seriously delayed. And this will incur excessive latency. And this excessive latency is due to excessive queuing delay. And the long latency will hurt the user experience, significantly. So hence, our focus in this paper is to address such excessive delay and support real-time traffic. So traditional wisdoms solve these problems through quality of service, traffic scheduling, or TCP control, flow control. For example, the QoS traffic scheduling prioritizes the real-time and the interactive traffic so that they can be delivered as soon as possible. However, this problem will fail when the traffic further increases. Why? Because the urgent traffic still need to compete for the limited bandwidth with other traffic. So the channel contention still exists. So how can we avoid such channel contention? The most intuitive solution would be to reserve part of the resources, which is used to real-time traffic only. For example, we can use OFDMA technique. The problem is, in this way, the delivery of other traffic will be degraded. So this is not what we want. Another intuitive solution would be to just exploit extra spectrum resources. For example, in the cellular network, the control messages is transmitted with the data messages concurrently in a separate frequency band. However, this is not available in the Wi-Fi system because of the scarcity of wireless spectrum. So, is there any way? Is there any other extra free transmission opportunities for the real-time traffic? So the answer is yes. So in fact, we can achieve this through wireless side channel design, which will create extra free transmission opportunities without impairing the other traffic. So in our design, we intentionally interfere the signal in the existing wireless channel, and the position of the interference indicated the data to be conveyed. So specifically, we refer the existing wireless channel as main channel to be differentiated with the side channel. For example, in this example, Alice is uploading some data through BitTorrent, and at the meantime, she wants to talk to Bob, who is nearby. So when a wireless link is occupied by the BitTorrent, then the Alice can add some interference which occupies the diagonal diagonal of this signal grid, and then the interference will be added to the main channel signals, and then they will be transmitted together. And in the AP side, it will decode the signal in the regular way and extract what he wants. And and also at the meantime, Bob can decode the text message by locating the interference. Similarly, if Alice wants to send a cartoon image, and she can encode the interference into different positions, for example, the last row of the signals, and then transmit it in a similar way. So in this way, you can see the side channel is built upon the existing channel, and there will be no extra spectrum needed. And the good thing is there is no channel contention at all. So the side channel design must meet 3 requirements. The first one is we don't want the main channel to be affected. So designing a side channel with at the cost of main channel degradation is apparently not what we want. So actually we can increase the transmit power to increase the SNR values to compensate the degradation caused by the interference. However, this effect is limited because the transmit power is limited by the FCC constraint. The second requirement is the High-Throughput. The throughput of the side channel needs to be high enough to support the real-time traffic. So High-Throughput means we need to add more. We need to add much patterned interference. But at the same time, it will hurt the main channel performance. Last, we need to decode the side channel because it's weak signal. It's interference. So in the traditional side channel design, they use very strong interference, such as energy spikes, as the interference. And this due to the constraint of the power, the number of interference is limited, and usually they only can append about 1 interference every several symbols. So the throughput is very low. It's around 100, 200K BPS. It's noted that the traditional side channel design is used to convey the coordination and the control messages, which doesn't necessarily require the very high throughput. But in our case, we want to support real-time traffic, so we want some higher throughput. So we will address these 3 requirements one by one. So first is transparency. So due to the inaccurate SNR estimation and the conservative nature of the rate adaptation approaches, so the actual SNR to select a specific data rate is usually higher than the required SNR to support this data rate. And the difference between these 2 values is called SNR margin, which provides an extra anti-interference capability. So our experiment shows that the SNR margin can be up to 5 dB. So by only exploiting a small portion of the SNR value, we can prevent the main channel from degradation. So to achieve high throughput, we just use energy erasure as the interference. So the position of the interference is convey the encoded data. And since we use energy erasure, there is no extra power introduced. So theoretically, we can add as much as possible, as much interference as possible to achieve higher throughput. So for example, this is the example of the Wi-Fi OFDM, the OFDM-based Wi-Fi physical layer. So in each OFDM symbol, the data is transmitted concurrently at closely spaced subcarriers, each of which corresponds to a specific frequency band. So if we want to encode binaural stream 11000, then what we do is to just erase the the subcarrier number 24, which is the decimal representation of the binary stream. So, and if we analyze the subcarrier energy, then in this OFDM symbol, the erased subcarrier, it has 0 power. Okay, so it can be identified. So the side channel throughput can be, if we denote K to be the number of subcarrier erasures per OFDM symbols, then the side channel throughput can be increased as K increases. For example, K equals to 1 is 1.25 Mbps data rate, and this number doubles when we raises 2. So, but we cannot indefinitely increase this number because we must to control the interference below the SNR margin. So we control the K to be at most 2. So, since we use energy erasure, to decode the side channel is equivalent to locating the erased subcarriers. So an intuitive approach is just as I said, is kind of energy-based approach. So basically what we do is to compute the amplitude or power of each subcarrier in one OFDM symbol and just collect the smallest one as the erased subcarrier. As you can see, this approach works good at high SNR scenarios, for example 20 dB. And you can see all the erased subcarriers which are marked in red, has a less power than other unerased subcarriers. So we can do it very well. However, this work doesn't work when the SNR deteriorates, because, for example, you can see in the 10 dB constellation, the signal points of the unerased subcarriers and the rest of the subcarriers, they mix it together, so we cannot simply detect it based on the energy. So this intuitive approaches can be improved by taking the statistics of the channel condition, channel noise into consideration. More specifically, even if a subcarrier doesn't have a minimum level of energy, we will still consider a non-zero probability for it to contain the pattern interference, which will be illustrated in the upcoming section. So this is the channel model, and the X and Y are the transmitted and received signal in the frequency domain. Well, the multipass fading, the distortion due to the multipass fading can be compensated by the frequency domain equalizer. So after our investigation, we found that the AWGN noise is the main reason for the misdetection. So we just propose our probabilistic detection approach. So first, the procedure of subcarrier erasure is equivalent to designating an extra constellation point, that is the origin, and in the frequency domain. So according to the Bayesian equation, the posterior probability for one subcarrier to contain the pattern interference can be written as this. Among this, the prior probability of the energy erasure is equals to K divided by the number of total number of subcarriers. And similarly, another prior probability can be derived as this. So these two numbers are constant, so we just ignore it. And we can simplify the equation like this. So, during our estimation, the AWGN channel is continuously being estimated. So this algorithm incurs additional computational overhead because this terminal needs to be calculated S plus 1 times, where S is the set of the constellation points used in the main channel. For example, if we use 64 quam, then this equation needs to be, this conditional probability needs to be computed 65 times, which is very time consuming. Well, we can simplify this equation. Actually, the side channel signals are very likely to be falsely classified as the main channel signals with the lowest part, which means the inner signals. So we simply just we don't calculate all 65 signals. We just calculate the signals, the main channel signals in that circle. So which is at most 5. So another challenge is of the side channel design is, we use energy erasure as the interference. So it's really hard to differentiate, to distinguish it from the background noise. So the existence of the side channel must be clearly clarified. Also, the destination of the side channel is also need to be clearly clarified. And in our first example, in the first animation, there are 2 destinations. The destination for main channel is the AP. The destination for the side channel is the Bob. So the channel, the destination of side channel may be different from that of main channel. So it's really challenging to to address this problem. So what we do is we just attach a preamble to the existing Wi-Fi frames. So the existence of this specific preamble indicates the availability of the side channel. And also we use the length of the idle period between the preamble and the regular Wi-Fi frames to indicate the destination address. So we use 2 short training sequences as our preamble. So we use short training sequences because they are native in Wi-Fi standard and it's very easy to detect. Also, the length of the short training sequence is set to 2 so that it's robust to channel distortion and also will not cause a false frame start. So we tried the resolution of the symbol length idle time calculation is around 10 Wi-Fi samples under 20 megahertz bandwidth. So that is 0.5 microseconds. So if we set the maximum idle periods to be 34, then we can have 68 devices to coexist and to use the side channel concurrently. So we implement our work onto the software-defined radio platform. And in our implementation, actually, the energy erasure procedure is quite simple. It's implemented through masking. And for example, in the frequency domain, the output of the PSK or QAM constellation point carries the amplitude and the phase information of at a specific data subcarrier. Therefore, if we are multiplying 0 with this phase information is equivalent to setting the amplitude to be 0. Or on the other hand, if we want to just disable side channel, we just set the mask to be all ones, then it's totally consistent with the existing Wi-Fi frame format. So this is our implementation, and the red, the block marked in red is the part to be added into the regular Wi-Fi physical layer. So, and also we implement our work on the software-defined radio platform, and we implement a total Wi-Fi consist transceivers, and we tune the SNR by adjusting the transmit gain of the sender side. So, and this is our first experiment. We tested the data transmission delay. And in our experiment, we set up multiple UDP sockets, and each of which transmits 1 KB long frames every around 100 milliseconds. So among them, one UDP traffic is marked as real-time traffic, and others are as background traffic. So from this figure, we can see the side channel delay is almost constant and is even slightly decreasing as the traffic increases. So this is and so this means the side channel can reduce the delay. So the key idea here is if there is more congestion, and congestion can create more transmission opportunities, which can reduce the delay. So, and this one is the side channel detection rate. So if we use just the BPSK and the QPSK, and when the SNR is greater than 10 dB, then the detection rate is around 100%. So it will usually, it achieves more than 90% accuracy in actual SNR scenarios. So this one shows the detection rate of a 9 Mbps rate. So it shows that the probabilistic approach can achieve up to 20% detection rate improvement over basic energy-based approach. So these two tables show the throughput. The first one shows the throughput of the side channel with one subcarrier being erased. So when the subcarrier when the SNR is better than around 10 dB, then the maximum data, the very high throughput can be achieved. And also in the first table, compared to erasing one subcarrier, at least another 3 dB is required in the channel SNR to maximize the data throughput. So this is the last figure. The last one shows the degradation of the main channel. So the y-axis is the BR increase. So you can see there are some SNR values under which the BR increase can be up to 3%, which is very high. But actually, this SNR values is not cannot happen in real scenarios. Why? Because under such SNR values, the BR of main channel without side channel, it can achieve around 30%, 40%. Is this is very high, and so this will not happen in real cases. So the right figure shows the BR increase in the real SNR, in actual SNR values. So it shows that less than 1% degradation in practical scenarios is caused by the side channel. So here's the summary. So what we do is to guarantee the latency of real-time traffic among congestion. So what we do is we use a wireless side channel, which built upon the existing channel, and also will not cause any or a minimum degradation on the main channel. And we propose a probabilistic approach to increase the detection accuracy, and a maximum of 2.5 Mbps data rate with less than 1% main channel degradation can be achieved in our design. So that's all. Thank you.